Okay, the purpose of this video is to talk about tensors. Some of you maybe have heard of a tensor before. I know we've thrown the word out a few times, but I wanted to formally define it and really convince you that you've been working with them your entire life, or at least since you've been able to count. So a tensor is a generalized term, and the beauty of mathematics is when we are able to generalize a term, we get many applications for the price of one. And in this case, the price of one name. What ends up happening is if you start having to name every single one of these objects, you very quickly run out of names and it gets confusing. So that's why the mathematical and physics community agreed upon, really the engineering community agreed upon this term tensor. So what is a tensor then? One definition I found is that it's a multi-dimensional array of numbers, and I found that definition very dissatisfying. So the definition that I would like to go with is a little bit more in depth, but I think I think it is more intuitive. So what a tensor, we would say a tensor represents a physical entity or an object I'll just put entity, which may be characterized by magnitude and multiple directions simultaneously. And if you're starting to think that perhaps this might have something to do with a vector, you would be correct. A vector is actually one kind of a tensor. What we would need to do is, again, like I said before, we need to be able to distinguish which tensor we're talking about. So the number of simultaneous directions is called the rank of the tensor. And what this does is it actually allows us to define how many different numbers or components are required to describe this entity or this object. Okay, so what we're going to do is we're going to play around in n-dimensional space. Okay, and let's just go ahead and start with the first number we can think of, which is 0. So there is such a thing as a rank 0 tensor. And this rank 0 tensor is described by n to the r numbers. So that would be n to the 0. Anything to the 0 is 1. So it's always defined by one number. And if you're thinking scalar, you are right. So this is something that has magnitude and no direction. So remember when we were talking about r being the number of simultaneous directions, there are no directions, so that makes sense that it's rank 0. And absolutely, this is a scalar. So I'm going to write all of the different terms here in this color right here. So this is a scalar. Okay. All right, let's move on to the next one, which is rank 1 tensor. So this one is described by n to the 1, which is equal to just n numbers. So if we were, say, in a plane, 2-dimensional space, then we're talking about 2 numbers. And it makes perfect sense that what we're talking about is something with a magnitude and direction. So the number of directions is 1 at one time. So indeed, we are talking about a vector. Okay? And what about a rank 2 tensor? Okay, so like before, described by n squared numbers. So if we were in, say, 4-dimensional space, right? It's so 4 squared, 16 numbers. And what we're talking about here physically is something with magnitude, direction, and a plane of action. So we have some object that has magnitude and direction, but we also have to define some plane that that vector lives on. And if this sounds so, and so if again, let's say that we were in 2-dimensional space, that's 4 quantities. We have to choose which some sort of plane of action, and this should start to sound very suspiciously like a matrix. And indeed, one example of a rank 2 tensor is a matrix. So specifically an n by n matrix. Okay. So now I would like to just point out, just in case you do hear this term, that a rank 2 tensor is also, I'll put this in a different color, is also referred to as a dyad. And when you get into higher level mathematics, you might hear something called a dyadic product. And just understand you're talking about a rank 2 tensor. Okay, so there we go. Now, one thing I do want to show you is an example, a specific example of a rank 2 tensor. So I took a picture from the internet here just because I didn't want to draw it. I don't want to give you a stick figure drawing, but in fluid dynamics is actually very, very, very important because this is where we get the Navier-Stokes equations, which describe fluid flow. This thing right here that I've drawn is called the stress tensor. So it can be a little bit weird to think about the magnitude, direction, and we need a plane of action. So I think it's easy to see, or easier at least to see from this picture, that what we're really talking about, the plane of action being what face are we talking about. So this box represents a little fluid element. So think of it as a very small, infinitesimally small width, height, and length. And so looking at that green face, the green face, the normal vector is pointing in the x direction. Okay, so this is the x face, if you want to think of it that way. We care really about the normal vector. So the x face, and I'm going to use the notation in the in this drawing here. So the x face, we will just start with the so the first index, or the first subscript, represents the face that we're on. So sigma x, the first x represents the face. I just told you that was x face. Sigma xx would be the vector pointing in the x direction on the x face. And if you can see it on here, I will make that darker. Sigma xx. Okay. The next term, the next component we're talking about, it seems that we should go in order. We're still on the x face, sigma xy, sigma xz. Okay. Now let's choose the y face. The y face is going to be the face where the normal vector points in the y direction. And that would be the reddish colored one. So sigma, we're on the y face, so y, x, sigma y, y, sigma y, z. And finally, we'll choose the blue face. The blue face, the normal vector is pointing in the z direction. So we have sigma zx, sigma zy, sigma zz. And what I would call this matrix, this tensor, is I would call this sigma ij. Okay, you should be familiar with this notation from the first discussion on Einstein summation notation. Now, one thing that you will see normally in the stress tensor is notice that when the subscripts are the same, I'm going to keep this as sigma. So I'll keep with my naming convention. But when the subscripts are different, what we're going to do is we're going to change that to the Greek letter tau. And what that actually represents is shear. And so all of these values actually mean something very specific. So sigma xx will keep, but then I'm going to change the next one to tau xy, tau xz. All right, the next face, I'm going to choose, so tau yx, sigma yy, tau yz. And finally, on the blue z face, I have tau zx, tau zy, sigma zz. And if you look at the diagonal, the main diagonal of this matrix, what you notice is that they're all sigmas. And we would actually call this normal stresses, which, by the way, is related to pressure. And all of the other terms, the tau terms, we would call these shear stresses. So if you hear the word stress tensor, you will know that it's a rank 2 tensor, and now you'll be familiar with it at least.